Hello, my name is Tom Salenza, and I'm a PhD student with the Bargerton Group at the University of Pennsylvania. And today I'll be talking to you about enhancing lift force at low Reynolds numbers with photophoretic levitation for porous 3D structures. So let's talk more about what this actually means. I want to start here with a picture of a material known as NanoCardboard. I'm going to go into more detail about what this actually is, but I just want you to take note of these channel-like structures that are created through microfabrication techniques shown in this image here. As a group, we discovered this levitation mechanism based on these channel-like structures. So if we have this microfabricated, very lightweight material that has enhanced properties, and then we deposit a carbon nanotube film on the bottom as shown, and then heat that up with incident light. We now create a temperature gradient for which the air wants to flow through those channels, building up pressure underneath the material and creating levitation. So essentially we can levitate this very small, thin material that can be built up to about 1 centimeter by 1 centimeter so far. And then if we could take that 2D material and turn it into a 3D geometry with this porosity in the sides, we can possibly build up pressure inside the material and force it out of a jet velocity, creating even higher lift forces and more pressure ranges at which we can operate. The original 2D planar structure levitation is optimized for lower pressure environments, but if we can do something like this, we might be able to move on to even atmospheric pressure, which is what a lot of the results I'm going to show include. And one day, if we can achieve these geometries in practice, we can deploy these on a surface like Mars, where we have about a 610 Pascal pressure. And that's actually ideal for the levitation mechanism. If we deploy an array of these microflyers, as we call them, with sensor and communication-based payloads on chips and whatnot, then we can relay the information back to the rover without the rover ever actually having to travel over this 20-kilometer, say, distance. We have possibilities for exploration are now much faster and more efficient, and possibly in places we never could before, aka up in the atmosphere of Mars, that is. I'm going to pause on the abstract here and let anyone want to read it if they want more details. It's also worth noting that these materials and levitation mechanism can work well in the mesosphere, which is another relatively unexplored region even on Earth. So because of the different pressures there are difficult for satellites and difficult for rockets and whatnot, and not really ideal for any flight mechanisms that we have right now. So another keynote. So I mentioned that the nanocardboard can achieve levitation, and I talked briefly about it, but let's go into more detail here. So here I have image A, which is a naked eye view of the nanocardboard, just if we were to look at it from afar. And if you zoom in, you can see that there's actually these channels in image B and the SEM images over to the right. There's these nanoscale channels. The entire material itself is on the micron scale for its thickness, about maybe say 50 microns. But the actual channels are obviously much smaller than that. The sheet thickness, let's say, so this is about maybe 2 sheets of material connected by this rectangular channel webbing, which ended up being about 50 nanometers in thickness. So it's all created through microfabrication techniques. We don't actually have to go into too many details there. I just want to provide the background on this material so that we can talk more about the simulations in detail. And like I said, if we shine light on the bottom of a CNT film that we deposit on the bottom, we end up with levitation, which is shown also in image D. It's actually a screenshot from a video from our paper that shows the levitation. And then image E is actually the pressure range in which this levitation mechanism is ideal. So this is the optimal range, and we're looking to obviously increase that. So like I said, this is a 2D material. That's also an important thing to know, is that this has only been done for 2D materials and not 3D, and that's what I'm looking to do. Some of the properties actually include a much higher stiffness and ultralight weight, which is great for levitation and maintaining shape, but it makes it very hard to fold, bend, or adhere these things and turn them into 3D structures. And like I said, they achieve this levitation through one version of the photophoretic force. So photophoretic force comes from this temperature gradient, moving the air through the channels and building up pressure. The other photophoretic levitation mechanism we employ uses a different material known as Mylar. So Mylar is a commercially available thin film. And if we coat the bottom with CNTs, again, this is very similar, but instead of having flow through channels, we actually have air molecules that get trapped in this heated up CNT layer, bounce around, gain velocity and temperature, and then leave with higher energies and essentially higher momentum. So if we have a change in momentum between when the incident gas molecules and when they leave, and you also have gas molecules on top leaving at a slower velocity. So if you think about, if you have a plate and you hit it harder from the bottom than you do from the top, it's going to move up. And that's essentially what's happening here, is you end up with a lift force. Just the words describing exactly what I just said in terms of creating this lift force from reflected gas molecules. But I'm also going to show a video here that will show the actual levitation mechanism. And it's a good time to explain that a fellow Parkinson group member will be presenting on this information in much more detail in terms of the controlled flight of Mylar discs. His name is Sam Azadi, and feel free to go check his work out. So we have here 2 discs that float, just to show that this is actually what it looks like. And if we can create 3D structures, we might be onto something a little bit more improved or more optimized. So what do we do to investigate this? Well, we started off with simple simulations. We start off with something that looks just like the original things that were performed, basically to confirm the solver's reliability. We wanted to make sure that if we set up this kind of unique setup that we will have, and I'll talk more about those conditions in a second, we wanted to make sure that it would actually work for, say, the simplest case we could think of, one that is definitely analytically shown before. Then we moved on to a nozzle where we have air flowing also through a disc, but then we have an angled wall that basically funnels it into a jet. We wanted to see if we can create this jet. Does this increase the lift force? And does this create a 3D version of the planar photophoretic levitation? In a case like this, you'd actually have to have carbon nanotubes layered on the inside, if you think about it, where we want the air to flow in to the geometry. And I just wanted to mention this so that it's kind of clear where the difference is here. It's not just the same exact structure. We now have the carbon nanotubes on the inside. And that'll be more important for something like this, where we have a porous cone, as I'm going to call it. This would actually be the same thing as the nozzle, but now we have air flowing in through every single wall of the surface. And this would be more like if the entire thing was made out of NanoCardboard or a porous version of Mylar, right? We can create porosity from, say, laser machining. So if we can create a porous material in this structure, you'd essentially have carbon nanotube film on the inside, building up air inside and out of the jet velocity, creating a lift force that might even be higher than anything we've achieved before. And then the goal one day, we also actually, I should mention, we'll be simulating some rocket shapes, which will eventually look like this. So this is a more rendered image than the actual schematics. I just wanted to show this so it kind of shows more of an application looking image where we have stacked microflyers that can be deployed. They have payload chips and antennas and whatnot. And you have flow through velocity through the side walls and out the jet velocity. So this is just a better example of what this might look like. And we actually will have a rocket simulation as well. And that's what I'm going to use to describe the boundary conditions. Because we're going to have a large, as I showed here, approximations of the flow through effect. And that's what we'll get to right now. So this may just look like a large box with pretty blue lines, but it's actually a streamline from the rocket shape simulation. So this is an entire airbox. These outside walls are considered walls. We have the inside wall here considered the axis of symmetry for the axisymmetric simulations. If we zoom in here, you can see that if we rotate around this axis here, we end up with a dome shape from the curved line and a tubular shape down the bottom, which gives us a slight rocket shape like I showed in the image before. Now, in order to create this flow-through effect, we actually made the outlet the outer surface of the rocket. So this is actually non-existent material in ANSYS. It's actually an empty space where very thin, make the outlet that top surface or outer surface, make the inlet the inner surface. Now you have air flowing into the rocket and funneling out with the jet velocity, traveling all around the airbox as shown with the streamlines, and then traveling back into the outlet, giving us about the same velocity as it actually went in. And this results in a very similar effect to what would be occurring with if we were to actually model all the channels and whatnot. So this is just a way of approximating this, and I will prove that it actually did work. So like I said, we have the inlet on the inner side and the outlet on the outer side. These are the most important boundary conditions, other than the axis of symmetry, which would, as I said, be this bottom surface here. This creates the airflow into the actual microflyers, allowing for the lift force to be created. If we vary the geometry and size, now we can actually characterize this lift force for given setups, given geometries, all different things. And if we can characterize it, then we have backup for these simulations being true. And like I said, the lift force that we actually take is the reaction force along the walls. So if we take the reaction force along all these walls, especially rotated in the axisymmetric case, we are essentially doing a force balance between the walls and the lift force, because there's the only two really things acting here. We'll take into account some gravity and weight when we talk about lift to weight, but for now we're just talking about the geometric effects. We're trying to figure out what is the best geometry to build in these simulations and which one would actually result in the highest lift force. Every other simulation was done the same way in terms of a geometry in an airbox, and then just drawn so that it can be axisymmetrically rotated around the axis, resulting in the full geometry. So that's why it was a cone and not, say, like a tetrahedron, because that's difficult to create in terms of the axis symmetry. And the axis symmetry is horizontal here just because of the chosen ANSYS fluent conditions. So let's start with the disk and the nozzle. So here we have the results for the disk. And as you can see, there's actually a transition at a certain inlet velocity. The axes here, inlet velocity and lift force, inlet velocity being the inlet conditions actually specified, the lift force being the reaction force taken along the walls. Fluent here in the legend is just to describe it as ANSYS fluent. It's the data that was taken from the simulation, and the theory is actually from equations that I will go over now. So if we have an equation here, this is actually a combination of the momentum theory, very similar and analogous to rotor blade momentum theory for thrust of a helicopter type blade, and the Stokes regime drag for the lower Reynolds regime. So you can see that there's a linear dependence on V for the Stokes regime, which is the lower Reynolds case. And that's what gives us that first part of the line here until this transition range. Then the quadratic dependency ends up taking over an approximation, and you get a different slope here for the higher Reynolds number regime. So that's important for most of these plots because all of them are pretty much going to follow this case. But this disk equation actually here perfectly fit our data to show that this simulation that very much approximates air flowing through a disk results in pretty accurate force values that we can take. I also want to mention what obviously Reynolds number is for those who might not know. This is a key important part in saying why the argument of the inlet velocity on the axis versus just putting Reynolds number can hold true. It depends on the linear dimension L and the velocity V. So these are all the variables here in the different equations. But V and L are important because we have the velocity, which would be the inlet velocity, but this is also changing throughout the geometry. So if it's a rocket, it's obviously going to be changing throughout the entire length, which would be your L. So we specify inlet velocity here because it's the easiest way to compare all the different geometries, since this will be a set value for each one, ranging from, as you can see here, 1 micron per second all the way up to 1 to 10 meters per second. So now let's add the nozzle to this plot. Now, if we have two different nozzles here, one going from 2 centimeters to 0.5 centimeters in radius, and one going from 2 centimeters to 1 centimeter in radius, we see that there's an increase in the lift force for the high Reynolds case. But if we look at the lower Reynolds number case, we now actually have no enhancement of force, which is not what we're looking for. We thought that the jet might actually help. The equation we used here that describes the data fits it pretty well. The only differences here is we now have different inlet and outlet conditions technically for in terms of this out and in. That means out means the actual jet velocity outlet circle, and the in means the inlet circle on the left here. So let's say that this would be the in, this would be the out over here. That's just different conditions. I don't want to confuse it with the word inlet and outlet, but that's essentially where this equation comes from. It's just a different comparison in terms of what's going on for the different velocities versus different parts of the nozzle. So now we know that we have no enhancement. So let's move on to a different shape. Let's try out the rocket shape. I kept the image here just to remind you what it looks like as we show the results here. So we actually, again, have changing of force with changing length, which is a key part that we wanted to see. So if we increase the length of the actual rocket, we get an increased force. And that's big because we know we can create tubes of, say, like a porous Mylar if we were basically just to wrap them around a mold or something like that. So if we can create this shape and make it longer, we actually have a better chance of achieving lift. The equation is slightly different here. For the force, we have now fitting parameters because the data does not fit as well for a complex geometry like this, where you have flow that's traveling along a long dome-like, from a dome-like shape and traveling along a long tube. So we had to include these fitting parameters, which help describe the data a little bit better and fit perfectly. And I'm going to talk more about those later. What I do want to emphasize is we also changed the diameter. And when we changed the diameter, we actually ended up seeing no increase in force. So that's why I included just the length plot here. When we changed the diameter, we actually ended up with no increase in force, but definitely an increase in force for the changing length. So that's what we want to see. We want to see this increase in force. What's going to be the best option? So we know that changing the diameter of a rocket, and possibly a cone for that matter, would not actually change anything for our results. So let's move on to the cone. The results are shown here again for changing length. Again, focusing on this because we just proved that there might not be any change in the force based on radius. So we now have 3 different lengths plotted here of a porous cone, the length being this basically height of the cone. It might be a little confusing, but I'll specify that there. Here we have a R in of 1 centimeter and an R out of 5 millimeters. Those are the 2 different inlet and outlet in terms of this big disk here and the jet velocity here. The cone is very similar to the rocket equation, just some slight differences in terms of the inlet conditions, but we still have the fitting parameters. So now let's talk about these fitting parameters. So I have a table here that shows all the fitting parameters that we've best fit the data so far. You can see I have the different geometries here: disk, nozzle, rocket, and cone. And then I have Earth, which is the higher pressure. And we actually ran these simulations at lower pressures as well. So what we've done so far is shown all the higher pressure simulations at standard atmospheric conditions. But we also ran them for lower atmospheric, lower pressure conditions like we would on Mars. And we actually see something very interesting. We have a C1 factor here of 10.92. So everything else is about 1 or even less, some smaller fractions. But the porous cone for the Stokes regime, which indicates the lower Reynolds number regime, because again, we have all these transition regions up to the higher Reynolds numbers, is actually 10 times greater than the actual force described by the disk equation, right? So the 16 mu RV here is describing a disk lift. Now we have 10 times that force, which is very good, a very good indication that we can achieve better lift. So now let's talk about the lift to weight. Here I have the Earth conditions for the lift to weight ratios of all the different geometries. And as you can see, the pink line is the porous cone, which achieves the highest lift to weight over all the other geometries at all velocities, and achieves a lift to weight ratio greater than 1 at an inlet velocity of over a millimeter per second, which we believe is very achievable on Earth at sea level. The same goes for Mars, where the porous cone outranks all the opponents and has a lift to weight ratio above 1, shown by the pink line, at about 1 centimeter per second. And this is on Mars. And again, the inlet velocity that we can actually achieve experimentally depends on this pressure. And at lower pressures, it's a higher inlet velocity. So again, this is another achievable inlet velocity that we think we can perform experimentally. And then just to show some of the more data that we did for the Mars simulation, since I haven't really shown much of it, I have the actual fitting parameters being tested here. So we have all different geometries at all different velocities, showing that the different equations still work and fit the data for the different pressures on Mars. So what's next? Well, we already have that lift to weight ratio showing promise for Martian flight. We also have the fact that the pressure range is now very possibly increased with the 3D geometries, considering most of these simulations were done for atmospheric conditions here on Earth. We also want to try simulating new geometries. So that might include spheres or something like that that might prove more advantageous than a porous cone. And we also want to emphasize that eventually we want to have these applications, including atmospheric sensing in the mesosphere and on Mars, like I said before. We've also begun experimental work on actually constructing these geometries. So if we have NanoCardboard shown here, and we try and glue it together, we've used some UV curing epoxies to essentially combine pieces. And the goal would eventually be to construct something like this. And obviously, this is a long ways away from just a right-angled fold, but this shows promise for what we might want to achieve in the future. So in conclusion, I've shown you photophoretic levitation of planar structures achieved by the Bargeton group. COVID-19 ended up halting all our experimental work, which resulted in the need to do these simulations. I didn't mention that, but it's important to note it here at the end that this is why we ended up doing simulations instead of jumping right to experimental work. These simulations were meant to expand on the 2D geometries to 3D geometries, increasing the pressure range and payloads we could achieve. And then we're looking to fabricate 3D geometries with experimental levitation tests as well. So this will be our future goals to validate our simulations to hopefully one day achieve the exploration applications shown here, obviously on Mars or in the mesosphere. And that would be all. Thank you very much to the University of Pennsylvania, Dr. Bargaton, my fellow Bargaton group members and co-authors, as well as my NSTGRO fellowship that supports me. And thank you for your attention and your time.